Okay, so let's talk about a couple of problems on that assignment that I just gave back that were missed quite a bit.
Wait, the force is going in?
One of them is question 19.
But it's a magnetic field. How is it magnetic field?
So on question 19, here's the setup. So you've got a wire with a current going in this direction. And you're told that you have an electron moving in this direction. Okay? So, let's make this right. So you have to use the right-hand rule twice. So the first thing that you have to do is you have to establish the direction of the magnetic field around the wire. So the current's going to your right. You curl your fingers. That means you're going to have dots up on top. So the magnetic field on the top side is coming out of it. Okay? Now, because it's an electron, if you want to use the left-hand rule, so this gets a little bit acrobatic. So the electron is going this way. The magnetic field is coming out of the page, so therefore the electron is going to be forced upward. Okay? Like this.
I don't know why I did that.
Now, some of you are saying, like, I got weird answers. Some of you are saying, like, into the page and out of the page. The electron, and this is where you kind of have to be able to visualize things on this unit. So it's traveling, like, in the plane of the page. So your only options are either up or down, okay? It's not going to be going into the page, out of the page, anything like that. Your only options are up or down. That's it. Okay? Can't happen. Those are your only options.
So we're back to two-dimensional physics.
And it was the same situation on question 15, okay? Which a large portion of this side of the room missed. So, especially 15B. So, you've got dots, right? And then you have a negatively charged particle moving into the field. See it, counter S?
What are you calling on me for, bud?
Well, because I think, I can't remember if you missed or not.
Yeah,
But here's
yeah,
the
you
story.
don't know. You wouldn't know.
So, on 15B, you've got, okay, hey, which direction is it gonna go? Well, the electrons coming up like this, so you got this action, right? The magnetic field is coming out of the page, so your fingers are pointing to the left, because it's an electron. So, it's gonna be going in that direction, okay? I'm just telling you, those are the two that were missed the most on that assignment, were those two questions right there. Okay, just for a little bit of clarification. And oddly enough, they both involved the fact that it was an electron and not a proton. Okay, so let's chit-chat about the assignment from yesterday, okay? So when you get to, like, for example, on like question 22.
Yeah?
So on 22, if you look at that one, you've got, okay, hey,
This way.
an electron or proton are moving in circular orbits in the magnetic field. The two particles at the same speed. Which particle takes more time to complete one orbit? Okay? So there's a couple of ways you can look at this.
So we're gonna go like this.
One is that what do the electron and proton have in common?
Bad.
They have the same charge, right? Now, the other thing about this is that they're at the same speed. So, because they're moving in circular orbits, what you assume is the magnetic field is what's creating the centripetal force. So that's gonna be QVB, and that's gonna be MV squared over
Is it clockwise?
R. So if you wanna shortcut this, you can cancel out one of these velocities, and you've got QB equals
It's all you need.
MV over R. So, because it's the same magnetic field, and they both have the same charge, the left side of the equation is the same. The speed is the same. Okay, cool. So, since this side has to be the same, as the mass increases, what has to happen to the radius? It has to increase as well. So the particle with the bigger mass is gonna have the bigger radius. Okay. And kind of 31 through 34 kind of have that same idea in terms of that relationship between magnetic field and the centripetal force. On 27, this is what we talked about yesterday. They were a little sketchy on the assumptions that you have to make on 27. And muons, we'll talk more about muons later once we get into like what's called the standard model of the universe. But, and it just gets weird. So what you're missing here is the fact that they don't tell you that the radius has to be the same, because that's the only way you can make a comparison, is if the radius stays the same. So if you look at, and you go back to this equation right here, where you set that magnetic field equal to the centripetal force, that's the whole point of that problem. So to a certain extent, it just works out to be a ratio. Be careful how you answer 36 in terms of what I'm about to tell you. Your answer to 36 is somewhat close to my age. Be careful how you answer that. I did that last in my AP chemistry class, and they said, what'd you get, like 1,400 or something like that?
You're positively ancient.
No,
One G
got
got 1,200.
Oh, once you got 1,200, yeah, that was it. It was like, really?
You're positively ancient.
Yeah, it was like, really? Now, let's talk about 44. So this is where circuits meet magnetic fields. Okay? So you want to find the magnitude, and there's two parts to your answer to 44. You want to find the magnitude, and you want to find the direction. Now, you have to go old school definition of current. Okay? So if you don't know which direction the current is moving in this circuit, you can't do anything else. So here's the question. Looking at how that battery is set up, is the current moving clockwise or counterclockwise? Clockwise. So the current's coming around like this. Now, the math is pretty simple on 45. You're just going to use F equals Bill. But what you have to be careful of, and this is where this is going to play out, in terms of that length, it's that distance that's going to be involved in that. So this is why they gave you that value of 10 centimeters. Notice that they didn't give you the horizontal distance. They're only talking about that value, which is in that magnetic field. So, now that you know that, if you look on that one, you've got a bunch of X's, which means what? What's the direction of the magnetic field? It's going in. So now, because of the fact that you're talking about current, we're viewing as positive charges, it works, just go with it. So the current's going to be going down, the magnetic field is going into the page. Once you establish that, then you can figure out what's going to happen. Oh, boom. current's going down, the magnetic field is going into the page. What's the direction on the force on the wire? To the right. Now, on 48, let me give you kind of a visual of what can happen with railgun. So I need to disconnect this and switch over to my other computer. So a visual of a railgun will help you on this problem.
Here we are.
Just use it. Yeah, I'm really Tesla. Yeah, this isn't that bad. I just should have done it already.
Okay, so this is a railgun that the Navy is working on developing. So here's the problem with railguns, is that they require a tremendous amount of electrical energy to make them work. The cool part about them is because of the fact that you're working with electricity, you can regulate the exact amount of current that goes into the system. Unlike like a traditional gunpowder thing, hey, there's some variance based upon gunpowder, does it explode, does it not? So railguns have the advantage of you can fine tune the exact amount of energy that you put into the system. So, with that said, and you can tell that if you look at all the cables in the back, that's a little bit of electricity.
Uses electricity instead of gun propellant. We've demonstrated that if you build it big enough, you can fire it and it works. Here at the DSST Expo, displaying the Navy's full-scale railgun prototype. A railgun is a gun that uses electricity instead of gun propellant to accelerate the system. And so what's new or exciting about that is it gives you much greater velocity than a powder gun can, which opens up the realm of how we use weapons. Because if you imagine an armature that's being accelerated down the barrel, it's going from 0 to Mach 6 in 10 milliseconds.
Yeah, 0 to Mach 6 in 10 milliseconds.
It's traveling so fast that you sort of see the slow motion video, so it looks very dramatic, but if you don't see the slow motion video, it'll just look like a quick flash. This is about the size of testing at the small scale. As you can see,
So that's
something this
that's
size
plates of
will
sheet
go through
metal.
6 plates of steel before it finally gets stopped. And if you can see what this does, imagine what something like this is going to do when it gets to its target. In the projectile, there will be a section here that will have the guidance and so that you can steer the projectile.
So
And there'll be a
look at
section
that
here
going through those plates of metal.
To fire a railgun, you need pulse power, what we call pulse power. Faster-based pulse power where you can store up the energy and then release it in about 10 milliseconds.
Hey, Berg, let's build one.
Before we got started, the size of the pulse power.
It'll take a lot of
that was required
electricity.
to fire a gun this size was about this size.
No, that's not
We've been
enough.
able to shrink the size of the pulse power for the same amount of energy to fire the gun from this down to this. So as you can see, that's a tremendous reduction in the size of pulse power. We're at the level where we're at sizes that are reasonable for integrating onto a ship. As you can see, we've demonstrated that if you build it big enough, you can fire it and it works. The next phase of the effort that we're in right now, the next generation after this, you will see an autoloader on the back. You'll see that it's being designed for shoot multiple rounds per minute. We've worked out all the controls, techniques with the pulse power to be able to fire multiple rounds per minute. Charging, releasing. That much power is quite a tremendous feat and accomplishment that we're engaged in proving and demonstrating here in the next 2 or 3 years. Did the calculations.
Okay. Now, Danny, bring the camera. Oh my God. Okay, so I'm going to show you a very, very, very small scale version of this concept. So coming back.
Wait.
There's,
I don't know, I eat all of my food with them. I'm as fat as this one.
no, it's not that impressive.
Let's get Charles.
Are you just gonna punch a hole in Preston from right there?
No.
What? It ain't that powerful.
Like I said, it's not that impressive. So what this is that you've got a magnet in between, and then you've got two rails on either side, hence the term railgun. So what's going to happen is that I'm going to throw a lot of electricity, as much as this thing can supply, and what's going to happen is that this going across here is going to complete the circuit. So as that completes the circuit, then what's going to happen is that when the circuit is completed, now you're going to have moving charges in a magnetic field. Once you have moving charges in a magnetic field, now you have a force, because force equals QVB. So if you don't have any current, then you can't have any forces, you can't have any movement. So initially I'm going to start off not much at all. I'm going to turn it on, and you get a little bit of movement. Okay? Ooh. Said it wasn't all that impressive. But
Pretty good gun.
if I crank it up a little bit more and then turn it on, okay? Now on that one, you actually, we got sparks. Ooh, pretty. Okay?
It up all the way.
So now think about this. From an atomic level, what had to happen to generate sparks?
Combustion.
Well, not necessarily combustion. At the end of the day, what did you have to make the electrons do?
Repel.
You had to make the electrons move out of their ground state into an excited state. They don't like it. They come back down and they emit photons. Okay? So the little sparkies that you saw was that not only did you have enough energy to make that begin to roll, you also had enough energy on an atomic level to take those electrons and create sparks. Now, as much as we can, even if I leave this thing on, as soon as I put that on, it begins to move because of the fact that what's happening as soon as you complete the circuit, you have electrons moving across. They're in the presence of a magnetic field. That creates a force. Boom, we get it rolling.
So what would happen if we like licked that?
Cohen, be my guest.
We did an experiment.
Can we please try that?
So,
Mr. Burkamp, you can look away.
no. So if I crank it up, kind of make it as high as we can get, okay? You get a little bit more.
I want to hear
That's
the
pretty much
box
as
humming.
max as we get.
I volunteer.
PC side.
Distribute.
It shorts out. Oh, never mind.
Actually,
Apparently
You
one
need a
side's
guidance
better than
system.
the other.
Yeah,
Oh,
I feel like that's not good.
so cranked up,
want to go in
what happens to the amount of,
You need a bigger bullet.
yeah, basically you get more and more sparks because you're putting more and more energy into the system. So that's why I said this is a very small version of it. But what you can do is, because you can adjust the amount of power that flows into the system,
They almost fell.
He was just fixing it.
because you can adjust the amount of current that goes into the system, you can adjust the acceleration of the system. Okay, back we go.